All right, so as you're probably well aware, I have pretty strong feelings about sequential versus holistic. I'm not a fan of sequential studies in mathematics. I think kids memorize forms, kick something back for a test 3 weeks later, 4 weeks later, lucky if they remember any of it. And certainly geometric, numerical, and all of those issues don't get discussed much in the sequential process. I don't think. I think that something like integration, for God's sakes, some classes aren't even getting there in the first semester of study. Not doing much with it, let alone trying to get actually what's going on geometrically and numerically and otherwise. So anyway, this is how I teach trig. I introduce it at the Algebra 1 level, at least a little bit, more so at the Algebra 2. Why? Because a lot of classes aren't even finishing the rudimentary fundamentals of trigonometry in a semester's worth of study. They're not getting past the unit circle, and which is being memorized anyway. In Algebra 2, I try to get some of the basics up and running, and I don't try to teach it all at one time. I just nip away at it, and so I'll show you that process right now. So to get to trig, I like to establish what pi represents. All right. I don't think folks are probably doing, rope around the Hawaiian punch can and doing some measuring at the elementary level. So I just draw 3 circles, various size, and I introduce this new concept of a new unit of measurement entitled the unit circle. And the radius in the unit circle is a radius that's 1 unit long. We don't attach inches or centimeter or anything else to it. It's one unit long in the unit circle. That's what the radius is. Now, yeah, language will improve over time as we talk about these things. But then I pose the question: how many radius lengths? Notice I'm not using the word radian. It's how many radius lengths are there? If we start measuring from here, and if we snip this and open it up, let's just open it up. How many of these distances will fit if I open that up? Now, let me open it up well here. So there's 1 marker length, and it'd be a little shorter. So there's 2, a little shorter. So there's 3. So that's about 3 marker lengths. It's got to be a little more than 3, 4, 5, 6. So 6 comes over here. So it's a little bit bigger than 6 radius lengths. Let's try this one. And see if this one is. This one is, oh, that's a little bit bigger. So we got to go a little bit bigger. There's 1 radius length. A little bit bigger. There's 2. There's 3. It's a little bit bigger than 3. We said, well, that's matching up. So I guess, that's roughly 6 radius lengths. Yeah. Wait, interesting. That's halfway around the circle, huh? Oh, wait a minute. Circles, lengths around the circle, that's circumference. Circumference is 2 pi r. Oh, I guess that's a radius length. In this case, it's 1. Then I guess all the way around is 6.28. Well, that makes sense. If that's 6.28, and I guess halfway around is, 3.14. Ah, okay, very important to know. And I guess if I'm turning the marker, that kind of represents angles, doesn't it? Angles. Yep, there's a certain angle. And I guess if I go all the way over here, how many degrees is that? 180. So I'm not trying to teach you here, but there's a new language system now for angles. I think I can start using that, because if we look at, making some triangles, let's put them inside a circle just for the heck of it. Well, there's an angle. Well, that distance right there, if I continue around, is just an arc length. It's a particular amount of the trip around that unit circle. So it looks like circumference can have its own language system for degrees, where we just said that 180 degrees matches up with 3.14 radius lengths. So I wonder what that is up there. Well, that's half, right? That's half of this trip. So looks like 90 degrees is pi over 2. So that could be, just a little chat on one day. And then I might ask them, well, how many degrees is 2 pi over 3? Talk about pi being 180, divided by 3 is a 60 degree. Double that's 120. And then I can start putting that on a worksheet. So here's a current worksheet after a month of practice. You can see there's questions if you freeze your screen, and then there's more questions and a little of this, a little of that. And I keep an eye on what the kids are learning and at what rate they're learning it at. And I try to salt in some challenging questions for the stronger students and students who are not moving at as quick a pace. They keep repeating the problems that we've covered since the start of the term and every day. So I would include this now as a problem on a worksheet where I just give them converting radius length measurements into degree measurements. Okay. Next day, we've been working with a lot of Pythagoras so far. So might come over here and already talked about, the new language system. So that can disappear. But, we've been working with Pythagoras and we don't look at it so much symbolically as we look at it organically. So there's 9, there's 49, and there's 58. So by definition, that distance is the square root of 58. So we've been doing a lot of Pythagorean, getting rid of this and then saying, okay, if that's the square root of 58, then what's this length? Well, if that's square root, that area is 58. 58 minus 9 and 49, and then you go, oh, the square root of 49, which is 7, is that length. So we practice that quite a bit. So we come over here and I start getting some definitions started. And again, I'm not trying to teach this in one day. This is a marathon. I would say probably 3 or 4 weeks before we get the fundamentals in front of us. And you'll see where that takes us at the end of this video. Over on the right, what I consider to be a fundamental. All right, so 3, 4, 5 triangle. People are pretty much familiar with that. We can do the 16, 9, 25, verify it. But the sine of A is 3/5, and the cosine of A is 4/5. And I don't even think I have to necessarily define, what just happened, because I want the numbers to speak for themselves. And then we'll talk about opposite over hypotenuse and and then eventually just height in the unit circle. That'll develop over time. So what would come from that question? If you can see the sine of angle A is 3/5, then what's the sine of angle A here? Well, we're hoping we got an 81. We got a 4, 81 minus 4 is 77. So square root of 77 with our Pythagorean work. And so the sine is the square root of 77 over 9. And we can start talking about ratios. Angle to ratio, trig, angle to ratio. That's going to be said every day now for the rest of the term. Then the cosine, 2 to 9, adjacent over hypotenuse, beginning to have a little bit of that conversation. All right, so what comes next? All right, so yeah, practicing that. I guess that's just a repeat of what I did over there. If I had some reason to, no, I don't think. Yeah, I guess that's just a repeat. So I can go up to the next thing that I would want to show. So since we did the equational line on day 1 and we've been doing it every day since, the kids have gotten very good at writing the equation of the line. So how do we write the equation of the line? Let's say through 4, 7. Well, we just write, x minus 4 plus 7, and we talk about subtraction as being the first and most important step in conversion. And so then, so from 4, 7, let's say we go to 9, 23, something like that. Well, 4 to 9, change an x of 5, 7 to 23, up 16, I think. Right. And so they've been doing that for the longest time. So now I'm going to start talking about time to angles, but the angles are going to be in radius length measurement, still avoiding the word radian. So 1903 pi over 2. So x minus 1903 puts us on to pi over 2, which is really on the unit circle now. 2023 is a change of what, 20 years, 20 years. 11 pi over 2 is 10 pi over 2, up from pi over 2, so 5 pi. Okay, let's make this to 2024, so I don't have to do any reducing right now. So that would have been a better choice. I could have done that on the fly. All right, and so now they've been doing this every day for about a week. You know, it's an algebra 2 class, and they're writing this equation. They don't know where I'm going to take them yet, but most of the kids are getting this right, which is good. All right, and so then next step is to really start to get into the unit circle work. I find that drawing the equilateral triangle is the best way to go, since we've done so much Pythagorean work. I think we're pretty much ready for this discussion. So all angles are 60 degrees. I bisect that angle, so therefore that's a 30-degree angle, especially if I erase this side of the triangle. And so then the first question I ask is, what's that length? And kids are pretty good at saying a half. Then I give them a minute to find that length. All right, so what do they have to do? See, a smaller circle might be helpful here. So we know that's 1, a half times a half is a fourth. Might have to show that. Some kids come in not knowing that. Okay, so this is 3/4. And therefore that's the square root of 3/4, which we whittle away down to root 3 over 2. And I give them a memorization sheet with all the numbers that I want them to know. Things like e to the 0.7 is 2. I fill up the sheet with things like that. 0.87 is what we use for a quick approximation. And so it doesn't look like if we were in decimals, 0.5 and 0.87. You know, 0.9 is 0.81 when you square it. 0.8 is 0.64. So let's just say it's somewhere in between, a little bit closer to 0.81. So why don't we call this 0.75? Oh yes, it's exactly what it was, wasn't it? 3/4 and a half. Yeah, I don't know. Anyway, we do a little work with that just so that they could start to get a feel for size. And now we've got ourselves a 60-degree triangle. Oh, 60 degrees. Well, I wonder what that is in radius lengths. Well, how many 60 degrees are there in a circle? Well, there's 6 of them, but in the top half, there's 3, right? 60, 60, 60. Correct me if I'm wrong, but I think that adds up to 180. So this is the first pi over 3. This is the second pi over 3. I guess this is the third chunk of 60 degrees. All right, so these are new concepts for the kids, and I'm not trying to teach it at this moment. I'm just planting seeds because I'm going to come back every day. And now we're ready to actually do some trig. And this usually takes about 4 or 5 practices before the kids actually get a little handle on it. All right, so what could we do? Well, we could say, all right, what's the mechanics of doing the sine of pi over 3? How are we going to do that? All right, well, the first thing we're going to do is draw pi, which is the top half of the circle. And we're going to break it up into 3 parts. And we just learned what the 60-degree triangle looks like. And I think I drop a perpendicular to the x-axis. And I think that's root 3 over 2. And this is a unit circle, and that's a half. We're familiar with that. So what's the sine of pi over 3? Opposite side divided by hypotenuse, which is root 3 over 2 divided by 1. All right, so that's how I begin doing that. The next one I might do, and I'll just do one here. And then these can be on every worksheet. And I can do a couple at the beginning of class, a couple at the end, and control the pace of learning. In other words, do it quickly. I have a rule of 4. I don't worry about that, what I just showed students, until 4 days from now. So if I showed that to them right now, 4 days from now, I want to see how the class is doing. So how would someone do the sine of, let's say this might be my next. I might change to pi over 6, but I'll keep it a pi over 3 right now. So how about we do 5 pi over 3? So what's the process here? Pi, top half of the circle, break it up into 3 equal parts. 1, 2, 3. We know those are chunks of 3. And I need 5, so I need the bottom half of the circle.
So there's 4, there's 5. What do? I draw a triangle perpendicular to the x-axis. I go from the circumference to the x-axis.
Really watch for kids who draw it the other way and correct them as quickly as you can. Okay, there'll be 1 or 2 kids in every class that, you know, draw their triangles, something like, what do? They do that. Right? And you explain to them, hey, historically, maybe that's how it could have been done, but it wasn't. So we are drawing our perpendiculars from the circumference to the x-axis each and every time. You might have to force that. All right, so you can see where this is going now. It takes a while for kids to get the negative, right? And then, of course, you might do 5 pi over 6. So now you have the kids here and you're doing 6 parts. And you know, you explain that if you tip this triangle sideways, you've got the 30-degree angle, you got half the hypotenuse. You start having those conversations. You'll work in cosine, maybe 11 pi over 6, something like that. So the kids eventually end up over here with a nice drawing, and you keep harping on nice drawings get good answers, nice drawings get good answers, and you work on their drawings, and pretty soon kids are starting to get those. At least that's been my experience, and you don't have to wait until, you do not have to wait until, oh God, I hope you're not coming in. Let me see another class. Are you coming in here? Oh, there's a class in here? What time do you guys get started?
2:30.
How much time does that give me? I got 5 minutes, 8 minutes? That's enough. Okay, you're gonna have to listen to me finish the video. All right, so I got 8 minutes, so let me hurry up here. So we've got ourselves the trig triangle, the famous 30, 60, 90. We're gonna introduce the 45s shortly thereafter. And one way to do it is just to see that a half and a half add up to 1 with that Pythagorean relationship. That allows you to talk about the square root of a half, square root of 1, square root of 2, which is 1 over root 2. Rationalizing gets your root 2 over 2. And a good approximation, 0.71, 0.71. I think kids can see 0.7 times 7, 0.49, close to a half. And start to get a feel for the 45s. All right, so eventually you can, you know, do the sine function. Might be nice just to have a circle here, just to say, follow my finger, the height's right, the height's right. It's not an exact relationship here, but it's enough to sell to them at this stage. And then you really got to develop the sine of 0 and the sine of pi over 2. And you really have to sell the cosine of 0, getting a max. I've only got a few minutes here, so I've got to really rush this. So finally getting to where I really want to get, which is putting it all together and actually graphing a trig function. And you can see the parts, I hope, match up here real quick. So here's a function. I'll do it as a cosine, and I'll also do it as a sine. And that way you can see why we started with those linear functions there before. All right, so pi over 2. So I want 1950 to act like pi over 2. And I want 2023. No, 1 revolution, so 2 pi has to be talked about. So 1 pi, 2 pi, 3, 4, 5, 6, 7 pi. So therefore, this is 7 pi plus pi over 2, which is 14 pi, I believe. So this is 15 pi over 2, I believe. 2023 is 15 pi over 2, which is 7 pi units from pi over 2. All right, so let's get the equation here, and then I'll let these students come in for their class. All right, so what's the most important y value in a trig function? The center line, so we got 35. What are we doing? We're going up 5 to get to 40. Okay, very logical. I'm going to do it as a sine function first. What do I see? I want 1950. So I'll write t for time minus 1950 plus pi over 2. Now they match up. Excuse me, but I got to do these quickly. And then what do we see? 1950 to 2023 is 73 years. And what happened in 73 years? 1 revolution, 2, 3.5 revolutions, 7 pi. All right, and so we start with that. If it was a cosine function, the cosine is of 0 is 1. So I can make 1950 act like a 0, and this is still the same. 2023 acting like 30. I'm sorry, 15 pi over 2.
Well, if that's gonna be 0, then this becomes just 7 pi. And so if I'm building from there, this becomes 7 pi. I'm rushing, I'm hoping I'm not getting all screwed up here. So I'm gonna call this 0 this time. So this is then 7 pi as to where I am on the circle. All right, so let's just write this thing and get out of here. All right, so this one is y equals 35. I'm still going on 5. It's cosine function this time. And I'm looking at making 1950 act like 0, so x minus 1950. And what do we have? We still have 3.5 revolutions, which is 7 pi. And that's still taking place in, I think I wrote the wrong thing down here. No, 73 years. Yeah, it was 70. Yep. So if you look at that, you'll see a lot of similarity. You'll see the equation of the line written very carefully and quickly. And so now kids are hopefully studying some trig before they get to it. Sorry. That was a 40-minute lecture. I didn't want to stop.